In this video, we discuss hash tables and generally the topic of managing more complex data in Java. Some of the important things that you are responsible for as a developer are designing and writing maintainable code, meaning at the function level or the module level or even the variable level, writing code that others can understand and that you can understand, code that can be maintained and edited and extended and reused at a later date, and also designing and writing maintainable code in an enterprise sense, meaning creating classes that can be inherited, that are written in a robust style, that follows some general rules of good design such as solid, SOLID, which we are not discussing in this video, but is a topic that you should look at on your own. You're also responsible for identifying and applying algorithms that are appropriate to the problem you're trying to solve, meaning you have to understand the problem you're solving, and you must find an algorithm that works to solve that problem. Sometimes that algorithm will be given to you by a systems analyst or another developer. Sometimes it's your responsibility to identify what algorithm is necessary to solve the problem. And then more along the topic of this video is identifying and applying appropriate data structures. At this level of our development, we are more interested in how to use the data structures from an introductory level. We're not going to get into aspects of efficiency and the nuances between different data structures. Those things can come later. If you can use a hash table, you can use a hash set, and you can use a hash map, and you can apply these technologies to other programming languages as well. If you're asked in a job interview, have you used a hash map? You can say, I have used a hash table, and they are very similar, and I can certainly adapt, and I'm interested and willing to do that. An excellent book along these lines is called Algorithms plus Data Structures equals Programs. I like it because it is written in a language agnostic level, meaning it doesn't talk about Java or C#. It's generally written about the science and the art of computer programming. So it gets you away from syntax and takes you through the types of data structures and how they can be used to solve problems. So it's an excellent read just to make you a better developer overall, not necessarily a better programmer. And if we look at it on Amazon, I'm always amused when we do this because you'll notice the paperback is $773.47. The hardcover is $10. I attribute that to the book selling bots that are out of control and poorly maintaining this data. So it's a pretty safe bet that that paperback is not worth $780, but for some reason the bots have bid it up to where that's what they think they can get for it. I don't know if people pay that price or not. I would certainly recommend spending the $10 on the hardcover, and yes, it may look like that. It may have a little bit of scruffiness to it because it is an older book, but it's written by a very well-respected computer scientist and author who actually invented a very popular programming language called Pascal that we used a lot to teach programming and do some development as well. So it's a well-written book. It's not dated, even though it might look old. It's still applicable to what we do, and I highly recommend it. From a very high level, the concept of a framework is a set of related classes that let you do something. There are frameworks for sending email, there are frameworks for managing websites, and in a general sense there is a framework for managing collections of data. So a collection in Java consists of a whole bunch of interfaces and classes that we can use to manage information inside a program. You could spend an entire semester studying this collection and identifying the appropriate data structure to use in the appropriate situation. We're not going to do that. We're going to focus on the hash table, but be aware that there is a thing called a collection framework. It exists in all modern programming languages, and a lot of the terminology that you see in Java also exists in other languages as well. Expect a lot of this to carry over. A popular interface that is used in a lot of the collection data structures is the map interface. You can see on the slide that I brought up a snippet of the Oracle documentation for Java describing the map interface. It's a parameterized interface, meaning you provide two data types when you initialize an instance of a class that implements this interface. And if you look at the bottom of the SNP, it lists all the implementing classes. Actually, that's not true. It lists all the known implementing classes, because you could certainly write your own class that implements this interface, not a problem. But we're particularly interested in things that hash, and there's in the list of all known implementing classes, hash map, and then there's ours, the hash table. Meaning that once you've learned this interface, once you've learned the methods that are defined in the interface, then any of these classes that use this interface, you are automatically an expert in. So learn the interface using one of these implementing classes, and you become experienced in all of the implementing classes, because we're programming to an interface. And that's very, very powerful. Again, learn one of these implementing classes and you automatically become very well versed in all of the implementing classes. Now, why are there so many implementing classes? Well, because there are nuances in the way we manage data. Do we want efficiency in memory allocation? Do we want efficiency in speed? Do we want things that we can easily insert into, things that we can more easily traverse, things that we can more easily delete, perhaps? So there's a lot of nuances, and the reason these data structures have evolved is to better implement those nuances throughout the framework. So our data structure of interest is the hash table, and hashing is mathematically converting some key, which could be a string, could be an integer, could be a complex object, into a number. That's what a hash function does. It takes some chunk of data, doesn't matter what it is, and makes it into a number. Now that number has a specific range. Okay, it might go from 0 to 2 billion or 0 to 4 billion or who knows what. But that function is guaranteed to take that given key value, whatever it is, and map it into a number in that range. Now, the larger the range, the less chance of collisions between keys, the less chance that two keys will map to the same number. We would strongly prefer that all of our keys map to different numbers, so we would like a very, very big range of results to come out of this hash function, and that's generally what we get. A 64-bit number, 128-bit number, a 512-bit number. Very large numbers. Hashing is done in a lot of applications of cybersecurity. We hash your password to make it unreadable, and we hash your password to make it into something that cannot be unhashed. Therefore, when we store your hashed password, it is gibberish, and it cannot be converted back to what you created as your password. It cannot be converted back to clear text. Therefore, hashing is important to us as data structure programmers, simply because we can hash into a unique value. Hashing is important to data security experts because we can hash it to something that cannot be unhashed. The hash function is interesting from an abstract perspective to us. We don't really care what the hash function is. We don't want to see the math. We're not going to study it. Were this a computer science class? Sure. We'd spend a couple weeks deriving hash functions, evaluating hash functions, looking for collisions. There are security issues with some hash functions because they tend to hash into a particular range of values that's very clustered, and sometimes the hash function can be defeated for that reason. But for our purposes, take away from this that there is a hash function and it converts any chunk of data into a number over a specific range of values, typically 128 bits, 512 bits, or even 64 bits sometimes. Okay, here's our data structure. You can see that according to the arrow in the little code snip on the slide, it implements an interface called map. Now, if you want to know more about the data structure, one thing you could do is go look up the map interface and see what all the neat things it can do. Let's look at the Oracle documentation for HashTable. So I'm clicking on the link on the slide. Here's the authoritative documentation for HashTable. I could scroll down through this and read. I'm more interested though at this point, because I know very little about the HashTable, in the interface. Now I'm going to tell you that there are three interfaces here. The one we're focusing on right now is map. The other two are not specifically related to managing data. We're going to leave those alone. If we click on the link for the map interface, we can see again that it is parameterized. It requires two parameters, k and v, which stand for key and value. We'll talk about that in a minute. The first thing I want to do is scroll down, and I want to know what methods are required by this interface. This tells me all the things that a hash table will be able to do, because I know a hash table implements this interface. Get. That looks terrific. If I pass it a key, whatever I have decided will be the key in this table, it will return the value associated with that key. That's a lookup. Give it a key, it returns the associated value. How does it do it? I have no idea. It doesn't matter. It works. Merge. I can merge two keys together. Put. I can put a value into the hash table. If I give it a key and a value, it will automatically hash the key and store the value into the hash table according to that hashed key. Remove. Delete a value from the hash table by the key associated with that value. Replace or update. I can give it a key and a value. If the key is already in the hash table, it will overwrite the value for that key. Once you've got a feel for all these neat little things that this interface provides, you have a feel for what a hash table can do for you. Before we start writing code specific to the hash table, take a step back and realize that there are, as we saw in the slide before, many different types of ways to store data. Simply, hash map, hash set, hash table. Hey, that's not simple at all. Which do we use? Should I use a hash map? Should I use a hash set? Should I use a hash table? Should I use some other bizarre data structure in the collection, in the framework? I don't know. So if I do a little research, I found a site called Java Infinite. I provided the link here. It provided a table, and it breaks down in pretty simple terms what a hash map can do, what a hash set can do, what a hash table can do. The one I'm primarily interested in right now, and the reason I chose the hash table to talk about, is circled on that code snip, on that screen snip rather. Hash table is synchronized, which means it's thread safe. Now that doesn't mean a lot to us now because we haven't talked about thread safety, but it's a big deal coming down the road because we have multiple processors in our computers and multiple threads running at the same time, and we want to use data structures that are thread safe. That will become important to us. So if someone says to you while you're standing in line at Chipotle, hey, why would you use a hash table over a hash map? You can say a hash table is thread safe, and that will answer their question, and you can go on and continue enjoying your burrito, because you don't have to worry about two threads clobbering the same data in the hash table, since Java advertises hash tables as being thread safe. That doesn't mean that you always use a hash table, but in my opinion, it means it should be your first choice if you don't have any other information. Notice in the screen snip, it says that a hash map is not synchronized, but it has better performance. If there's a situation where, hey, I know this will always run in a single thread, and I know there will never be a multi-threaded application derived from this class, okay, maybe I need that performance, maybe I should use a hash map. If I don't know the answer to that question, and I'm not sure, let's stick with the hash table. Parameterized class, we use the little less than, greater than delimiters. It kind of looks like HTML from that perspective, but it's just the Java syntax to define a parameterized data type. The K can be any letter, but we use K to indicate keys. The V can be any letter, we just use V to indicate values, and those are simply placeholders anyway. We're going to replace those with legitimate data types. When you declare an object of type hash table, you define what data type the key is by replacing the K with that data type. You define what data type the value is by replacing the V with that data type. Why are we doing this? Well, we need to manage information. We have the collections framework, and we can abstract this even further and say that it's kind of like a very little tiny limited database, because we can do key value associations and look up things according to keys. And hopefully that triggers a little bell in the back of your mind that doing lookups and sorting things by keys is exactly what we're doing when we mess with a real database. So a hash table, a hash map, all those hashy things can be thought of as little tiny in-memory databases that are very useful for relatively small amounts of information. You wouldn't load all the eBay transactions in the world into a hash table. First of all, there wouldn't be enough memory, and second of all, it would take forever to run. But if you have lesser things, 100 things, 1,000 things, maybe 1,000,000 things, depending on how much memory you have, a hash table is a good application. This is an oblique or general reference back to the map interface that we saw before. These are the things that the map interface supports, just written in a more abstract manner. And these kind of apply to most data structures that we would want to use. What would we want to do with a hash table? Well, we certainly want to put things in it. We certainly want to delete things from it again. The big deal, okay, the big idea, we want to search by key. Instead of having to iterate over the entire hash table element by element, we can do a key search. We need to see how big it is. Is it getting too big? Is it small enough? We need to erase it if we want to start over. We need to step through it one item at a time. So we're not doing a search by key in this instance. We're processing each element as it comes in a linear fashion, in whatever order the hash table has stored those elements, or we want to convert it to an array list or convert it to some other data type to do something with it. So in my experience, those are some of the more popular things that you would do with a hash table and pretty much any data structure really, except the search by key part. A question you should be able to answer in your own mind and also in line at Chipotle is, why do we do this when we already have an array list? An array list, and I'm flipping back one slide. An array list lets you add items. An array list lets you remove items. An array list lets you check the size. An array list lets you erase all the elements. An array list lets you iterate over all the elements. And an array list lets you convert it to another type, which is typically just an array. The only thing we can't do, evidently, in an array list that we can do in a hash table is search by key. That pretty much appears to be the only thing we can't do. Now, this is a generalized broad list. There may be some other nuances that aren't available as well. But you need to have an idea in your own mind and an ability to discuss the topic of why you picked the data structure that you picked. So if we don't need to search by key, maybe an array list is a better choice, because I will tell you that an array list is much more efficient speed-wise and memory-wise than a hash table is. Way better. So if you care about efficiency and you don't care about key searches, an array list may be the right choice. And I guarantee you that you will be asked in your career, why did you choose this data structure? Why did you choose a hash table? Why did you choose a hash map? Why did you choose an array list? And be ready to explain that. A good tip to follow is to put that information in your documentation somewhere. When you introduce that data structure into your application, I use a hash map because. I use an array list because. And that gives you a little trail of breadcrumbs, and that lets the people that come after you, that read your code, understand why you made the choice that you made. Well, if a hash table is way more powerful than an array list, why don't we use it every time we need a collection? Why don't we just throw away array lists and throw away arrays and use a hash table for everything? Hopefully the answer is a little bit clear to you now, that we need efficiency sometimes over capability. Sometimes we don't need to search by key. Let's use an array list. We gain speed, we gain memory efficiency. We want to start with the most efficient data type that solves our problem. We don't use a bazooka to kill a mosquito, because we can get a fly swatter to do that. So we start out with the most efficient solution, and if necessary, we can scale up later, and we haven't wasted time and wasted CPU cycles and wasted memory in the meantime. Let's write some code. I have opened Eclipse, and I have created a project. You should be following along with me. The project is called In-Class Module 10. I created a package called main with the lowercase m, because packages start with a lowercase letter by convention. And I created a class called main. I don't need a secondary class right now. I'm going to do everything in the main just to demonstrate hash tables. And in the main, I typed in this line of code. And you'll see right away that it has a red squiggle under the word hash table, which I did intentionally, and we'll fix that in a moment. If you haven't done this yet, you should stop the video and you should catch up with me. Create your project, create your class, create your main method, type in this line of code. It should look familiar from the reading that you did. You can see that the key value in this hash table is a string, and the value data type is also a string. I'll put a little comment in here. Remember, in the slides and in the general description of a hash table data structure, we use K and V as our parameterized data types. We replace those with legitimate data types when we declare the object. So this is a little more complex than we've seen before. We haven't done parameterized data types before, but we're just declaring an object of type MyTable. I'm sorry, an object called MyTable of type HashTable. And as I said a moment ago, you will have a squiggle if you typed it exactly the same way I did. I did this on purpose because I always do it wrong and it makes me nuts. I think the T should be capitalized because I think it's two words, hash and table. The hash map data structure has a capital M, so why doesn't the hash table have a capital T? I don't know. Makes me nuts. I do it wrong, and then I realize it's wrong, and sometimes I'll let Eclipse fix it. You'll notice Eclipse realizes that there is a thing called a hash table with a lowercase t, and it offers to change that in my code to hash table with a lowercase t. I can take that fix. This might be one of the first times that we are actually not taking the first fix. And then do I have to do that again? Yes, I do. All right, the squiggles are gone. Also notice that there is an import up here. Import java.util.hashtable, that's the definition of the hashtable class. Now your project knows what a hashtable class is and it can deal with your variable declaration. We still have a warning. As we expect, the warning is that we created something called MyTable and we are not doing anything with it, and that's fine because it's correct. We haven't done anything with it, but by now you should have a little chunk of code following along with me with no squiggles, and we're ready to roll and do neat things with the MyTable.